Alright, hey everyone, we left you off with how the solar system works, how it operates with elliptical orbits, and the speed of the planets, and even the timing of the planets based on their distance from the sun. But that still didn't confirm heliocentric versus geocentric until this guy came along.
Yeah, Galileo is pretty important in this whole idea. He was the first person to take a telescope and look at Jupiter and to see that there were actually moons that were going around it. That fact led him to believe that maybe we weren't the center of the universe, maybe that all objects don't go around the Earth.
So if you look at Jupiter now, you can see that there's Jupiter and then there's 4 dots right next to it. And if we look at Jupiter the next day, the dots have shifted, they've shifted again, and every single day that you look through a telescope at Jupiter, you're going to see those moons in different positions. Like you said, orbiting Jupiter and not us.
That's exactly what Galileo determined when he looked at this.
Another thing he used was the phases of Venus. Since Venus goes through phases like our own moon, that must mean that Venus must be inside of us. So you can see a half-filled Venus versus see the full Venus on the back side of the sun. So that phase transition, and again, you needed a telescope to see this, was only because Venus is inside our orbit. And the fact that the moon wasn't perfect either. If all the things in heavens were supposed to be perfect, the moon had mountains and ridges and wasn't a perfectly spherical body. So now we know we're in a heliocentric world. We need to know why objects move the way they do. And that took the next big giant in physics, Newton.
Newton is considered one of the smartest guys to ever walk the earth. And he came up with this idea called the universal law of gravitation. And what that basically says, well, is in the formula here.
So that if you have 2 masses, and those masses are separated by a distance, they will be attracted to each other with their own mutual gravity. They will pull together over time.
And that goes for every object in the universe.
So the 2 of us are attracted to each other.
No.
That's what the formula says.
I know.
And I can't help but be attracted to you because of your mass. The thing that keeps me from sliding across this floor right now is the friction of the floor. But if we were in space like these baseballs, it would not take much time at all for our own gravities to pull us together. Only about 3 days before the 2 become 1.
Yeah. And if we go back to the formula, that's exactly what it shows. It shows that as masses get larger and larger, since both masses are on top, the gravitational attraction will increase. If the objects are more distant, being in the divisor there, it actually decreases the amount of gravity between the 2.
And what it does is follow something called the inverse square law, which means that the further you get away, it doesn't just drop off by half or a third. If you can see in that picture at the bottom, you can see the light going through that first area at the bottom is pretty intense. But as the light gets further out, the light spreads out and goes through less and less area. So the factor of light, or gravity in this case, will drop by a factor of 4 at twice the distance away. It'll drop by a factor of 9 when you get 3 times further away. What if you get 5 times further away?
25 times less.
So if I want to be less attracted to you, all I need to do is move.
It's not a bad idea.
So Newton said that, all right, this is the reason why the planets move the way they do. They follow this universal gravity law. Okay, but that still doesn't answer why do 2 masses actually pull together. And that's what the next smartest guy you probably ever knew, Einstein. And what Einstein said was that he envisioned space as a fabric of space and time merged together. And objects follow curves in this space-time, and that's what we observe as gravity. So if you put a mass onto this trampoline, you can see it warps the fabric of the trampoline. If you put a second mass in that fabric, what'd you see?
I saw gravitational attraction. I saw one mass move towards the other based on the way that fabric was warped.
So the reason that 2 things attract is because they actually follow the curves and the warping of the space around them. Now, our trampoline here is a 2-dimensional representation of space-time, but this happens in all 3 dimensions.
So you can imagine coming in from any direction, the same thing would happen.
Okay, so there's this warp in space. Masses warp space, and the more massive you are, the more you're going to warp the space around you. But that still doesn't tell me why a planet orbits. I think that all planets should then just crash into the moon should crash into Earth. We should crash into the sun.
Well, sure. I mean, that would happen if space was exactly like this fabric, but it's not exactly like this fabric. One thing we have here that we don't have in space is friction.
True. So we won't slow down as we roll around this fabric, but that means we must be moving. So why do the planets orbit? Well, what is that picture on the right showing you?
Oh, that's the shuttle taking off.
Oh. So it's not a missile launch or a missile attack. That's actually people riding the space shuttle into space. Mm-hmm. And one of the first things you notice is that we don't just shoot straight up to go into space. We actually start to curve. Newton had this idea with his cannon.
So with Newton's cannon, what you do is you take a projectile, very much like the space shuttle here, and you fire it out of the cannon.
So bam.
And it immediately starts to take a downward turn because of gravity.
Okay, well, let's put more gunpowder in that cannon. Bam.
All right. So, okay, a little bit more gunpowder. It might actually reach the edge of that picture there, which means it would start to fall over the side.
Okay, let's put more gunpowder in there. Bam.
So now what we have is we have projectile motion, and it's actually starting to move around the curvature of the Earth. If we put enough gunpowder in it,
boom,
it might actually make it all the way around. And even though it's falling the entire time, it makes it all the way around and completes an orbit.
So orbit, the reason things orbit is that they're falling towards some central mass. You said that mass is pulling on the projectile with the force of gravity. It's just never hitting that central object.
And if you can continue to do that, you can continue to orbit.
So for the space station, if you fire fast enough, you can actually orbit the Earth in about 90 minutes.
And continue to do so for a very long time.
As long as there's no friction.
Right.
So now back to our warping of space-time. This time we have that central mass, but we're giving our projectiles, our planets, some horizontal motion. Send it around that central mass and not right into it.
As those objects orbit that central mass, there's a certain speed that they do it because of the amount of mass that's there.
So you're saying if that central mass gets bigger, so this time we're going to add two masses in the center, and you saw them attract each other again.
And orbit one another.
And orbit for a tiny bit. But now when we send those smaller planets around the stars, you can see them whipping around the stars much faster.
Yeah, they're going to go faster because they need to maintain a faster speed, not to fall into the center of mass. And they're going to try to do that naturally because of inertia. But with friction here, they're eventually going to be pulled in. But if you didn't have friction, you could maintain that orbit for a very, very long time.
And you can see the marbles that go far away from our central mass, they actually travel slower than when they get close. So why Mercury goes around in 88 days is because it's so close to the sun and it whips around that warp in space-time. So Newton's laws, along with some Einstein ideas, explain why things do what they do in space. The first thing is the universal law of gravity.
So the universal law of gravity is saying that two masses are attracted to one another, and if you increase the mass, you increase the gravity. At the same time, if you increase the distance, you decrease the amount of gravity squared.
And then once things are in space and they are moving, objects will obey what we call their inertia. That's his first law, and everyone can repeat that. That if I have a block sitting here on ice and it's not moving, it's at rest, so it will sit and stay at rest. Newton's second law says, well, what happens when you apply a force to that mass? Well, if I apply a force to that mass, describe what you see.
Well, it's no longer sitting.
And what about the speed?
It's increasing as I increase, well, it's increasing as I add force.
And once the force disappears, the object's in motion, so it wants to
stay in motion
until some outside force acts on it.
And notice when it stopped, the little dummy stopped applying a force, he remained at rest.
So what we have here is we have a central mass that's bigger than the orbiting planet, and if I give zero velocity to my planet, due to their attraction, the planet pulls into the sun.
That is right.
That's not really fun to do. But if I give my planet some velocity, and I make sure that velocity is tangent to the circle, it can now orbit the star and not fall into it. You can actually see the ellipse that it creates because of that motion. It doesn't create circular motion. And you can see the planet get fast when it goes close to the star and slow when it gets far away, just like Kepler said.
Yeah, and you can see the center of gravity too.
And based on Newton's third law, says for every force there's always an equal and opposite force. So the sun here pulls on the planet. What's the equal and opposite force?
It's the planet pulling on the sun.
So the planet pulls back on the sun. So if you watch this, you can actually see the sun try to go towards the planet, and the star wobbles. We talked about this when we said, how do we find exoplanets? This is why. Because one force has an equal and opposite force. In this case, the force is making the planet go in a circle and change its direction every single second. So Kepler gave us the how planets move. Newton and Einstein came up with the why planets move. So make sure you understand how Newton's laws affect planetary motion.